Our topic today is wave data analysis. In this topic, we're going to look at how we analyze raw data collected, and it's different from our previous discussion about small amplitude wave theory, whereby we already know the properties of the wave such as wave height and wave period. Here, wave data analysis is taking the raw measured data in order to analyze the wave period, wave data, and other properties. Now, the average energy of the wave train is proportional to the variance, which is given by this expression, okay, which basically is a summation of all the components of the wave inside it, where A is the magnitude of each of the component. So essentially, in order to do this, we will have to integrate the energy spectrum from 0 to infinity. Now, since the energy spectrum is a continuous spectrum, right, so the individual component, right, will have their own energy density. In this case, the individual component, the energy density is given by A squared over 2, which pretty much is the same here, right? So essentially what we are highlighting here is that the energy spectrum is proportional to the square of the amplitude. The square of the amplitude of the individual wave component. If we carry out the decomposition and calculate the energy spectrum, then we will get a plot that looks something like this, whereby we have frequency on the horizontal axis. Typically, we may also plot the period, which is the inverse, right? And on the vertical axis, we have the total energy or power. So if we plot out, then we may get a profile that looks like this, which tells us that the observation has wave with frequency as low as this, and it has wave with frequency as high as this. The dominant wave frequency is in this region and in this region, whereby the wave period is about 5.4 seconds and in this case 8.7 seconds. So in this particular set of data, then we may identify the dominant wave period to be 5.4 seconds. If the analysis is for wave height, then we also use the same approach to identify what is the significant wave height. Typically, the significant wave period will be approximately 0.95 of the spectral peak period that we obtain from the frequency domain analysis. Meanwhile, the maximum wave period, the T110 and T130, they are usually quite close to one another, and they are usually about 1.2 of the average wave period as mentioned. In our previous discussion, we focused on analysis of the wave height and the wave period, which basically uses the same approach. We are also going to highlight here that there's one more component or information that's very important, which is the direction of the wave. So in most coastal application, we will also be interested to know what is the predominant direction of the wave. Where is the wave coming from? So in order to do that, we will have to analyze the directional wave spectra so that we are able to identify which direction that the wave energy density is the highest.